Thank you. Okay, so as Jim presented, I'm going to discuss the NVMe Over Fabrics Offload in this talk, and also I'll finalize with a nice use case where we use the offload for also having efficient NVMe emulation, which is more useful in cloud environment. So in terms of introduction, and part of this was already presented also last year, so some recap and status update. So NVMe, as an introduction, is a well-defined standard with a lot of community involvement. All the hardware interface of the NVMe is standardized. The register sets are standardized, so it's pretty easy for deployment. You use the native kernel and standard NVMe driver. No need for any vendor driver. You don't need frequent updates, all those benefits. The standardization actually focuses on performance and efficiency, also efficient mapping to RDMA with NVMe Over Fabrics, as well as other transport. You can see that there's very well support for multi-core processing with the ability to define multiple submission queues and completion queues that can be assigned per core or per process or whatever the user finds efficient. And then we have the NVMe Over Fabrics. Why do we need it? So we don't keep the storage captive in the server. We don't, in terms of scale out with using the existing infrastructure like PCI, SAS, and SATA, the scale is much less than using the network. It's also a well-defined standard. NVMe standard was defined in September 2014 and published in 2016. So also this was standardized. Just a quick example of a use case for NVMe and NVMe Over Fabrics. We can see here a two-tier based storage system. So on the first tier, the clients can connect to the controllers through any of the Fabric storage protocols like iSCSI with TCP or iSCSI over RDMA with ICER or Fiber Channel and or NVMe Over Fabrics actually. And the controllers can connect to the JBOFs themselves also to either one of those protocols, and NVMe Over Fabrics is one of them, which maps very nicely to an actual NVMe disk that resides on the JBOF. The standard came with a very nice mapping between the IR objects, the NVMe objects, and the Fabric objects. A submission queue is mapped very nicely to a queued pair, a send queue. The completion queue of the NVMe is mapped very nicely to the queued pair receive queue plus completion queue. Whenever a host would like to access the NVMe, it submits a submission queue, rings the doorbell. With NVMe Over Fabrics, the same submission queue entry is being encapsulated. It is called the capsule. And then also ringing the doorbell for sending that operation over the network. In terms of the device completing the submission queue entry and writing the completion queue entry and then sending an interrupt or allowing polling. In the NVMe Over Fabric case, the NVMe Over Fabrics target sends a completion queue entry capsule to the initiator, generate a completion queue entry at the initiator on the receive queue, and also an interrupt or a poll. In terms of the data exchange, so with NVMe, it's a local PCI data exchange. With NVMe over Fabrics, it's over the fabric with RDMA read-write or inline immediate with up to 8K of data. So in terms of the work that have been done is that there is a community NVMe over Fabrics target in the kernel. It works in the block layer, so you can see here that in our case where we use the ConnectX or our SoC Bluefield, clients can connect remotely to the NVMe over Fabrics target. We have here the target driver. It can connect to any local block device. It is using the block layer to actually map the storage device. And the block layer can support any. It can be NVMe actually device. It can be just any SCSI device. It can be a local file, or it can be also a remote device that is exposed as a block device. Of course, the NVMe mapping is the most efficient, and this is where we propose to do the offload whenever there is an NVMe to NVMe connectivity. Okay, so in a nutshell, how things work. So if we look at this diagram, here we have the initiator. This is the fabric, the RDMA fabric. This is the NVMe Over Fabrics offload device. Again, it can be the ConnectX or Bluefield. This is the local CPU of the system. Here we have, of the target system, here we have the actual NVMe flash and the host or appliance memory subsystem, where we keep the I/O queues, the completion queues, and intermediate data buffer of the actual NVMe to NVMe operation. So in terms of the example that is being illustrated here, this is an I/O read request being sent by the NVMe initiator. It is sent to the NVMe target. The device, the offload engine, gets this I/O read request, generates a submission queue entry towards the NVMe device. So it actually performs a DMA write from the device to the location of the submission queue of the NVMe, filling the submission queue entry with a read request. Then it performs a peer-to-peer PCI transaction, writing to the doorbell of that I/O queue, of that submission queue, to actually let the NVMe know that there is a new submission queue entry. Then the following goes on in parallel. The NVMe device responds to the doorbell, fetches the submission queue entry, and in parallel, our offload engine polls the completion queue of the submission queue to see if the I/O request that was sent, the submission queue entry that was sent, was fulfilled. Once the NVMe got the submission queue entry, it sees that it is a read. It performs a DMA write into the host memory, into the designated buffer, writing the data that was requested to be read. And completes with filling a completion queue entry for that submission queue entry of the read request. And of course, the offload engines detect that. Once it was detected, the offload engine that is aware of the location of the buffer for that submission queue entry that was posted, it DMA reads this from the host memory, and RDMA writes it into the initiator, into the client memory, finalizing with a send, which, as defined in the NVMe Over Fabrics protocol, which marks the completion of the I/O read request. So this is in a nutshell the flow that is going on. As you can see in this flow, we did not use any CPU. The CPU was orchestrating all of that in terms of the control path, but was not doing any operation during the data path operation itself. We are still using, indeed, the memory and the memory bandwidth of the server or the appliance, or the target appliance, in terms of the queues and the data buffer for intermediate memory location. Once we will see more NVMEs with CMB, controller memory buffers, on the NVMe controller, then we can also utilize that memory for that end, for the queues and for the staging memory. So once we have that, we would not need to consume not just CPU, but also a memory bandwidth from the appliance, from the target system. In terms of verbs, and again, this is a proposal. We have an RFC in place. We are still evaluating the ways to correctly expose that, either verbs, also through SPDK. But the current proposal is that we should support namespace remapping. So the front-end namespace ID and the actual back-end controller namespace ID should not be the same. We can support some level of virtualization there. Once we turn on the offload, then the I/O queues and the completion queues of the NVMe are in hardware ownership. So we can't allow both the driver and the offload engine to use the same I/O queues. Of course, they can use separate I/O queues and completion queues. And also the offloaded objects of the NVMe Over Fabrics of the RDMA portion, also those objects, once we turn on the offload, they are in the ownership of the device. So we will see in the following slides which objects are in use, but you can see here that we are using the IBV Shrek shared receive queue object, the QPs and the completion queues of that QPs for the communication, and that's basically it. Of course, if you are using the non-offloaded commands, then it's transparent to the software. The software is managing them as usual. We try to describe all of that in one slide. What is the model? How the API objects are being used. Again, today we mapped it to verbs, and we might change it to SPDK. It's still under some thoughts, but in terms of the object, we'll see a very similar object model. And what we are using today is that we have an object that is the shared receive queue. That object is actually describing the intermediate buffer that is being used for the transaction, as we've seen in the previous slide in the example. For the I/O read, we are using the buffer from the host memory to actually read the data from the NVMe into that buffer and then send it out to the fabric. So we are using the shared receive queue object in order to articulate that buffer. We have an NVMe, we have established an NVMe Over Fabrics controller object. So this controller object is associated with an intermediate buffer, which is the Shrek. And this object basically maps or is aware where is the location, what are the addresses of the actual NVMe device I/O queues and submission queues. So it maps directly to a specific backend with a specific namespace ID. So once we have those objects in place, the shared receive queue and the NVMe Over Fabrics controller, which is associated already with an existing in-place NVMe backend controller and driver, we can start with a connection. So we establish a QP and its send queue. We associate that QP with a Shrek, the same way we associated QP with a Shrek today, and can use that for actually running NVMe Over Fabrics RDMA protocol on top. So this is mainly in high level the model. In terms of the Verbs flow, so we start with identification. Always when you bring up your application, you would like to discover what hardware, what kind of elements do you have. So we've added support for querying which devices are there, what offload capabilities the devices support. Then we create the shared receive queue, as I described. This is the first element. It describes the intermediate buffer. Then we have the NVMe controller. That's the NVMe backend. It is mapped to the I/O queues and completion queues and doorbell of the actual NVMe controller. Then we create a mapping of namespaces, as I described. We are virtualizing the namespaces, so there is a front-end namespace and the actual device backend namespace. So this is the mapping that we do. We tell the controller what is the front-end namespace ID and the backend namespace ID. And then we can start with the communication. So we create the QP associated with the Shrek, modify its state to a state where it is now offloading NVMe over Fabrics, and now we can run the NVMe-oF protocol in an offload fashion. So as you can see, we have software running, CPU running for establishing those objects, associating them, and then for data path beyond the modify QP, it is all hardware flow. I can go quickly on the Verbs changes, and again, some of it might change. This is just a proposal. We also consider, as I said, to adopt it with the SPDK. So as I described, the first stage is to get the capabilities. So here we can query the capabilities. In this proposal, it is an extension of the device, the IBV device attribute. So we can see here there's what is the total backend controllers we can support, adapter-wise, what is the max number for specific device, namespaces, what is the size of the staging buffer that we can support, size of the capsule, size of the I/O queues that we can support in the offload manner, the I/O queues of the NVMe, and that's mainly it. So this is in terms of capabilities. The create Shrek, so the modification of the create Shrek here should allow us to allocate the staging buffer. So we can see here that we have here the description of the staging buffer address and length, and also memory key. So the staging buffer also goes through the usual registration in Verbs, the IBV regmr. So that's mainly it for the Shrek. This is the creation of the controller object, create NVMe controller. We can see here that the attributes here and here, the attributes are the actual addresses of the I/O queues, the submission queue, the completion queue, and their corresponding doorbells. The actual addresses are maintained here in that object. So we fetch those, if it's SPDK who is managing the actual NVMe device, we get those details from the SPDK. And we end up with the mapping of the namespace IDs. So we have the front-end namespace ID mapped to the actual NVMe device namespace ID, which is the backend. And as you recall, the controller is already associated on creation time with the Shrek, so that association was already made. And that's the last phase, is to enable the QP. We modify the QP as we do for send operation. We modify the QP to RTS, ready to send, which is the last state to have the QP ready for communication. In NVMe Over Fabric state, we actually modify it to be offload ready. In terms of error handling and exceptions, so for non-offloaded objects, it's the same. But for offloaded, now that the objects are being managed by the hardware, so in terms of when you post an NVMe Over Fabrics request, say the initiator sent to the target side a request and the target is in offload mode. So if there is some completion queue entry with an error on the QP that sits on the target side, this is handled because the QP and the CQ is now in the ownership of the offload engine. The software can't transparently or easily see that error, so that's why we actually need to notify the software. Now we are moving those objects from software ownership to hardware ownership, and we are generating a new asynchronous event to let the software know that now there is an error and the exception flow is being managed by the software. That's mainly the point for the exceptions. And to finalize, this is the NVMe emulation feature that we support that can be accelerated using the NVMe Over Fabrics. So in this case, if we look at if this is the host and this is the NIC or the smart NIC, we can see here that for the host, we expose a PCI function, which is an NVMe. And that PCI function that is exposed by actually the NIC is, of course, an emulation of an NVMe actual device. So on the host, we can basically run only the NVMe driver. We don't need to run any RDMA stack, any RDMA subsystem. We don't see on the PCI, we don't need to enumerate any NICs on the PCI. We only enumerate the NVMe controller. And those, the emulated hardware of that controller is basically mapped to the NIC. So all the admin queue operations, all those control flows are handled by the NIC itself. If it's an SoC, it can be managed by the ARMs that reside or the processors that reside on the SoC. If the host is a VM, then those admin commands can be managed by the hypervisor. So the NIC can tunnel those operations into the SDK of the NVMe emulation that runs on the hypervisor. That's just a simple use case. And in terms of the data path, so we can see here that if this is an IO queue in the emulator side, this goes through the hardware IO processor and then goes directly to the fabric if it is capable. So in terms of NVMe Over Fabrics, if the use case is mapping an NVMe emulated device to a remote device through the NVMe Over Fabric protocol, then we are using a similar acceleration that we have for the target that I presented in the previous slides. We use a similar offload approach for this initiator side. So basically, submission queue entries that are posted to the emulated NVMe are now being sent into the fabric through our hardware engine without any software intervention, either, of course, from the host itself or from the SoC or the hypervisor. So we see very nice efficiency there. And the last slide is about the SDK. So the SDK is mainly on top of SPDK. So we actually able to map an NVMe emulated device into the SPDK virtual block device, the VBDev. So essentially, you can map any emulated NVMe device to any SPDK block device. And the block device can be, of course, NVMe Over Fabrics over RDMA, which in that case we can offload completely to the hardware. But it can also be mapped to any other VBDev, NVMe Over Fabrics over TCP, or any Linux POSIX AIO. If you have VBDev for iSCSI or for other protocols, you can use that. Of course, this means that also data path will go through either the hypervisor or the SoC CPUs to get into the VBDev of SPDK. But this is in case of other than NVMe Over Fabrics protocol, which, as I shown, is easier to offload to the hardware. And the nice thing about it is that in terms of the stack that is being ran, you have the whole SPDK stack at your proposal, so you can virtualize services like RAID or LVM. You can do that underneath the hood, so the host sees an emulated NVMe device, and on the SoC or on the hypervisor, you can run whatever you want in terms of the stack. You can do RAID, you can do LVM, and we also merged that with existing storage offloads that we already have, like erasure coding and signature handover CRC. And once we'll have more, then of course we can enjoy more of those. That's it. Any questions? Yeah.
A simple question, or maybe I have a simple question. Would it make sense simply to put together these two devices into one physical device? Having
to NVMe, you mean? Or?
Having a HCA with some M2 slots and put in the NVMe on this thing, and just completely avoid the PCI transactions for.
Well, you still need them talking together, so it's a peer-to-peer transaction. You mean the HCA and the NVMe?
No, I mean, when you would have an HCA which would get extended by a flash memory, when you just put the memory on the HCA and have some M2 slot maybe to put in just the.
You mean combine the NVMe with the HCA?
Yeah.
Well, we do also support in our SoC a PCI switch. So essentially.
Yeah, sure. Right.
So essentially, you can use
if
that
you would
switch.
Have a PCI switch on your HCA,
we do.
You could do that, right?
We do, but it requires a specific platform. It's not general use case server. But yes, we support that.
Okay. Thank you.
But still, there's the intermediate buffer that is required. So
yeah, sure. If you don't have that on your device, you could still use the host memory, or if you have it on your device, you could.
So with the SoC, we do have a local GRAM attached. So we can use that as an intermediate buffer. But once we will have devices, NVMe devices with CMB, that will also save memory bus bandwidth.
Thank you.
Sure. Hi, Paul.
Could you go back one slide? Is there any thought about adding libfabric to that little cluster of capsules at the bottom there?
You mean like NVMe over fabrics over libfabrics? That's what you refer to? Like what wire protocol are you proposing?
It depends on the definition of when you say NVMe over fabrics, which is sort of verbs oriented, right? Fair?
But remember that libfabrics is just a means to get to an RDMA API. So in our case, when we offload to hardware, we don't care what is the software API.
It is an RDMA API all unto itself. It doesn't necessarily run over verbs. It runs over multiple fabrics. I guess what I'm asking is...
But it's a user space API.
That's true.
So for the initiator side, it's running over the standard verbs.
That's true. That's true. Anyway, so the real question is, are we thinking about extending this to include other APIs other than just verbs?
So as I said, we have an RFC in place. It is based on verbs. We're also considering using SPDK. It might be more natural space for that, for those APIs. We are open to accepting others. If you have proposal how to attach that to LibFabrics, we can gladly work with Sean or you guys. But the community, it's all upstream, it's all submission free. So if you have patches, if you have proposals, submit an RFC and we can
I was just wondering if
consider.
there's been any discussion about that inside the NVMe community.
Not that I'm aware of.
Okay, thanks.
But anyhow, the wire protocol is an NVMe over Fabrics wire protocol. It's not something that is vendor
I can
specific.
answer as well. I mean, if you saw some of the slides that Phil presented on the initiator side, so NVMe Over Fabrics initiator already has multiple transports. So it has an RDMA, which runs today over like a verbs-based RDMA.
Right.
But it has fiber channel, it has TCP. There's nothing preventing you from plugging in a different transport into NVMe Over Fabrics on both the initiator side or into the SPDK for target development.
That's what I was getting
Yes,
at.
there's nothing preventing that. I have one question, and it's around, do you know if there's any, or if there are any off-the-shelf appliances now that use your offloaded capability with actual NVMe drives that are purchasable, or if not, when you see those arriving in the ecosystem?
So in terms of appliances, yes, we do have appliances supported with our SoC. But as I shown, this is a server. You can just have a server with ConnectX-6, for example, and use that.
Yeah, I was just wondering if like there was some, you know, a NetApp or some storage vendor that says, okay, you can just buy this appliance, plug it into your fabric, and it's a NVMe storage target.
Yes, of course. We do have partners.
NVMe-oF
Sorry, go ahead.
offers NVMe-oF over Rocky and over IB. NVMe over Fabric now offers a target over Rocky and over IB. So that already exists like for 2 years now. Yeah, it uses his offload capability. Not the ConnectX-6, it uses different chip, but it uses ConnectX, one of the 5.
But it doesn't have yet the offloaded stuff that he was showing.
No, no.
There are companies with like E8 storage, for example, that I think that the showcase already their models that use the offload. There's several more. E8.
There are more, but I'm not sure I can mention in public.
Yeah, I was just wondering if there was something available or if kind of when the time frame when appliances would start showing up in storage.
Yeah, so there are a couple in public. Some others going to show.
Also, we are working with large cloud providers that obviously we can't say in public. Thank you.